All right, so welcome back. I hope you all had a good coffee break. Our next talk is from Shaoshan Liu. Dr. Shaoshan Liu's background is a unique combination of technology, entrepreneurship, and public policy, which enables him to take on great global challenges. On technology, Dr. Liu has published 4 textbooks, more than 100 research papers, and holds more than 150 patents in autonomous systems. On entrepreneurship, Dr. Shaoshan Liu is CEO of PerceptIn and has commercially deployed autonomous micromobility services in the US, Europe, Japan, and China, etc. On public policy, Dr. Liu has served on the World Economic Forum's panel on industry response to government procurement policy and is leading the autonomous machine computing roadmap under IEEE International Roadmap of Devices and Systems, IRDS. And so with that, I will turn it back over to Shaoshan. You can boot me off of screen share.
Great. Oh, thank you so much for the invitation. So today since the workshop's name, it's a mind gap. So I'm going to share my story about autonomous machine computing. Especially I want to highlight that to mind the talent gap. That's what we have observed in the past 5-6 years as lack of talents in this industry. So since you guys are attending RSS, I assume that you guys are the lucky ones in this generation, because I do believe that robotics is the biggest opportunity in the next 2 to 3 decades. Kind of different from the previous speakers, and I actually did my PhD, then I went into the industry. Then I resumed research after I launched the startup. It's quite an interesting story. I'll explain why. So it's more like a transition from industry to research in my case. But so let's get started. And first of all, the reason that I work on autonomous machine computing, it's because of the talent gap, and I will explain why. So I don't need to do a deep dive on this, but the market size, you guys can see, it's huge growth potential. If you look at the annual growth rate per year for the robotic sector, including autonomous driving, it's tremendous growth that we have not observed since the mobile computing era. But sadly, the problem that we have observed today is all the autonomous machines that we use are still not able to perform very interesting tasks. They just perform very basic tasks of moving from point A to point B. And my conclusion on that, or my observation on that, is because of lack of brain power to enable them to do very interesting tasks. The solution is, why not just design a universal computer or computer architecture for different kind of robots? And that's my the motivation for my work. Let's go back to history. It's quite fun to consult history when it comes to technology development. Remember, I guess most of you guys are not old enough to hold a Nokia phone. But back then, if you had a Nokia phone, it's pretty basic feature phones. What was the market size back then? $10 billion. Is it small? No, it's quite big, $10 billion. If you examine a Nokia phone, you see that 90% of the compute power go into basic function, encoding, decoding, and so on. Only 10% of the compute power go into end applications. But then today, if you look at the phone again, it's an $800 billion market size. 90% of the compute power actually go into end application, YouTube that you watch on the phone, Instagram, Twitter, Facebook, and so on. Only 10% of the compute power goes into the basic functions. So that's the observations that I have made in the past few years. So for robots today, if you look at the current design of robotic brains, 90% of the compute power go into the basic functions, meaning perception, localization, planning, control, and so on. Only a very small percentage go into application, probably 10% of the compute power. You can reserve that for very interesting applications. What we want to achieve for the industry to thrive is to have roughly 80 to 90% of compute power go into application, so that you guys can think of very smart applications for the robots to create market value. Then we serve only 20% of the compute power for the basic functions. So that's what we are looking forward to. Very short summary of my work started with autonomous vehicles. So here's a very simple diagram to illustrate autonomous vehicles. By the way, for the each slide, if there's a reference, I will leave it at the bottom of the page. If later on you're interested in a piece of work, you can check it out. But basically, if you look at the stack for a autonomous vehicle, it's quite complex. You have sensing components, perception, decision. You need a operating system to bind everything together. You need a hardware platform. Then every single robot, it's actually a mobile system, meaning that you need a cloud to support it. For example, for autonomous driving cloud, you need to create the so-called high definition map. You need to do a lot of simulation. You need model training. You need data storage, and so on. So it's not a simple system. We are only have scratched the surface of this whole industry. There could be many startups in the future to do cloud computing for robots, for example. So let's go back to our story, my own story. So when we launched the startup, we tried to develop very affordable autonomous vehicles. But then compute was the main bottleneck. We had three options. First is to optimize commercial off-the-shelf mobile SoC that turns out to be the cheapest, most affordable option. And it's backward compatible, meaning that you write the code once. If there's a next generation chip, you just port it. It's easy. So that's our favorite option. Option two is to buy specialized autonomous driving computing systems. Back then, I'm talking about 2017, 2018, it could cost you 20, 30,000 per piece. That's way over the price tag of our vehicles. So it may not be a viable option. Option three, to develop our proprietary autonomous driving compute systems. As a startup, we would not want to go that route because it's very expensive. It's going to burn up our cash reserve. So let's see what happens. Option one, we managed to port a low-speed autonomous vehicle workload on a Snapdragon 820 cell phone that would cost you about $300, $400. But the problem is that it's not good enough for autonomous vehicles, maybe good enough for autonomous robots, but not vehicles. If you look at the distribution, some workload is very suitable for the DSP. Some workload is very suitable for the CPU and the rest of it, the GPU. So the modern heterogeneous SoC are actually quite good, but not good enough for autonomous vehicles for a few reasons. For that few reasons, if you're interested, you can check out the papers down there. We have a very detailed explanation why it's not suitable. But a short answer is that we are trying to optimize multiple workloads at the same time, whereas a cell phone processor actually has only one foreground workload at one time. So they optimize for that foreground workload. But for autonomous vehicles, you have many modules. Any one of those modules can become your bottleneck. So procurement of specialized computing, no, it's too expensive. It's very simple. As a startup, we just simply cannot afford it. In addition to that, it's a black box. So you cannot, in a lot the situation, you cannot even change the program inside. So it's not for us. So we had to, it's painful, but we had to build our own system, compute system. Ended up, we did a lot of exploration, spent about a year and a half and delay our product shipment. But we ended up with quite a good compute system. But at the same time, it's quite complex. Let's look at the requirements for that system. Latency, throughput, you guys are familiar. If you use ROS, right, you want the throughput to be at least 10 hertz. So that's one constraint. There's energy and thermal constraint. Since we run on electric vehicles, so the amount of power you burn really matters. You can drop the operation time from 10 hours to 7 hours, for example, if you don't do a good job on optimizing your energy efficiency. And cost, of course, is a very important issue. We want to provide service to, with the cost of $1 per chip, say a 1 mile chip, you charge people $1, for example. Then safety, you need proactive mechanism and reactive mechanism to protect the safety of the autonomous vehicle, and of course, the passengers and the pedestrians. So you are facing a lot of design constraints. It's so complex. Ended up, we built a system that consists of a FPGA-based sensor synchronization unit so that we can hardware synchronize all different kinds of sensors. Then we have a GPU for deep learning-based workloads and the CPU for control-based workloads. Here's the the layout of the system. If you're interested, there's a paper down there, but it's quite a complex system. But we managed to drop the cost down below our affordable range, and the performance good enough. It meets all the constraints. The bad side or the downside is it took us about 18 months to develop and then burned up a lot of our budget because of there's no available or good enough compute system out there for us. But when we look at this problem, the essence of the problem, it's really talent supply. If you ask a algorithm engineer to do a lot of system optimization, it might be challenging. If you ask a systems engineer to understand all algorithms, it might be challenging. So it's the two different parties here. You need to mingle these two parties very well to develop a very good system. So the learning curve, even for myself, I came from systems background, the learning curve would take a year or two. But if we summarize the compute patterns, it's quite interesting. It looks like a traditional, if you guys came from computer architecture background, it looks like a traditional data flow architecture because each module, especially at the front end, will provide a lot of data coming into the pipeline. Then each stage of pipeline will fuse down the data by an order of magnitude, for example. And at the end, only a very simple control signal will come out. So it follows a strict data flow pattern. If we look at the left side, it's a autonomous vehicle computation graph. On the right side, it's a robot vacuum, but the pattern's quite similar. So that makes us think if we can develop a good enough abstraction for computing, then the algorithm engineer can only focus on the application of the robot. They can connect all the modules together without worrying about optimizing the systems down below the algorithm layer. And the systems engineer can focus on the down below part, which is which module fits best into which compute unit, whether it meets all the performance constraint, energy constraint, and so on. So some traits that we have observed in autonomous machine computing. First trait, continuous inputs provide abundant parallelism. At the beginning of the pipeline, you have LiDAR data coming in, you have vision data coming in, you have sonar. Each one is independent, so you can do a lot of parallelism over there. Flexible dependencies. If you are a consumer node, while you depend on the producer node, but if there's one frame that's dropped, there's nothing you can do. You consume the next frame. So there's no strong dependency here. Deterministic data communication, unlike traditional computer architecture workloads, the data you send is quite deterministic, meaning that you know how much amount of buffer you need to allocate. At the end, there's pretty much no loops because they are dead graphs for these kind of machines. Or if there's a loop, you can easily break it into different decks. That makes the abstraction quite clear and quite concise. We even develop a very simple functional programming based language for that. For example, to describe the figure on the right side, basically you input a few required statements. So the system will tell you whether they can meet the requirement. For example, you want to require the camera to produce 320 by 240 frame resolution with frame rate more than 30 hertz. If the system cannot do it, it will tell you cannot do it. But if it can do it, we'll move to the next required statement. But at the end, there are only 3 lines of code to connect all the modules together into a computation graph or data flow graph. Then the program will just run. So that's the beauty. If we could do that, then the algorithm engineers can focus on this abstraction layer, and the systems engineer can focus on whatever that's down below to optimize the whole system. If we can do that, then the whole industry will leapfrog forward because today, at least in our company, we spend a lot of time working on systems issues. We spend a lot of time working on algorithm issues. So algorithm engineers, a lot of times they have to pick up system skills. Systems engineer, they have to pick up algorithm skills. But the crossover always comes with a steep learning curve. And the step further, if there's any systems research in the room, you can develop hardware accelerators for different kind of modules. Because if you look at robotic functions, there aren't that many robotic basic blocks. If you look at the basic building blocks, for one thing is sensing. That's people use different kind of sensors, so that's one thing. Perception, that's the second thing. But the way you perceive the world for different kind of robot, there are a lot of similarities. So a lot of algorithm can be used for different kind of robotic perception. Localization, most people use SLAM or LiDAR-based mapping algorithms and so on. There's a few common building blocks. Planning control, again, a few common building blocks. If we can figure out the common building blocks, or 90% of the common building blocks, and for those building blocks, we provide accelerators or hardware assisted computation methods, then the whole computation pipeline becomes quite simple. So in summary of the first part of the talk is that we need a very good abstraction for autonomous machine computing. Otherwise, it's a hassle for algorithm engineers to cross over into systems domain. Vice versa. A lot of times the system engineers are forced to learn about algorithm stuff, but they were not trained to do it. So we are facing a very steep learning curve. There are three architectures that I think I summarized that could help this industry. First one is data flow, we just covered in the previous few slides. Second one is vector graph. I think a lot of you guys are very familiar with vector graph. Vector graph can do very good optimization, can be a good abstraction for localization, can do planning, can do mapping, but can it be a universal abstraction for different kinds of robots? We'll see. We're still doing research in that domain. And the third one is end-to-end learning. Still early today, but Tesla is moving towards that direction with enormous amount of data available. So end-to-end learning would be a beautiful architecture as well. If at the end, we just have to use two transformer networks, one in the front end, one in the back end, that's a beautiful abstraction as well. That will save a lot of hassle for algorithm engineers. But we'll see which one would be the default computer architecture or abstraction for autonomous machine computing. So what we want to talk about today, or what I want to talk about today, is really the talent gap, which in this paper we illustrate what we have seen in the industry, the painful process of training engineers who are from the algorithm background to provide them with systems knowledge. Or for people coming from the system background, we have to ramp them up in the algorithm domain. But if you ask people in the school, this survey we did with a leading research university in China, if we ask the incoming graduate student, what kind of area you want to go on, you want to go into algorithm or you want to go into systems research, 80%, surprising 80% would choose algorithm because first of all, easier to get a job. That's quite understandable given the recent boom of deep learning and robotics. High pay, I think that's a key reason, economic incentive. And fairly easy to learn because you have to understand a few networks, run it through Python, then from that, it's easy to go through the interview process. The 20% that stay with system domain because of passion, they like to do computer architecture, compiler work. It's challenging. They've seen a lot of system work are quite challenging. The ramp up cycle, although very long, but once you are having fun in that domain, you would find it very challenging. And at the end, it's fun. So that ratio is a bit scary for companies like us because eventually when you want to ship the product, a lot of things are, all of the work and efforts are in the systems engineering domain. So what can we do to close the gap if we see a gap today? If people go into research, they prefer to do computer vision research over system research. What can we do? First, simple solution, pay them more, higher pay for systems engineer, quick and dirty, but I don't think it's sustainable. I don't think the company are able to cover that given the economic situation that's faced by a lot of startups. Solution two is to evolve our education system to expose people in both algorithms and in systems research, such that people focusing on developing algorithm can understand computer architecture, compiler techniques, and so on. But its long-term benefits are obvious, but it won't solve any near-term problems that are faced by the industry. Solution three, I'm not sure if Vijay is here today, but I think the work done by him, Brian, and his group, TinyML-like efforts, because that really bridges the algorithm side and the system side. And a framework like that's easy to learn, fun to use, but once you get your hands on TinyML, you pretty much understand what kind of algorithms you are optimizing for and what are the system's requirement to make sure that your code is very light and very efficient. Solution 4, which is what I'm working on today, is to break the world into 2 parts. The high-level language part, which we have just covered, that can be used by programmers to develop robotic applications. Again, as I mentioned at the very beginning of the talk, today we are still focusing on building basic building blocks for robots. So these robots can only perform very basic functions. There's no interesting application yet. For example, for autonomous vehicle, why not using a autonomous vehicles go to different places to provide medical services? To me, that's an interesting application that unlocks the potential of the robot instead of just sending a food package from point A to point B. That's one application, but is that quite interesting? How big is the market? We don't know. But we are still not yet ready to develop very interesting application for 2 reasons. First, due to talent supply, the lack of talents in the industry. Second, the lack of computing power to free up enough compute power for interesting applications, just like what we have experienced in the mobile phone era. But to do that, we need to have the bottom part of the world. You need to isolate the basic operations, be it sensing, localization, planning control, perception, computer vision, and so on. Then on top of that, you can, or below that, you can develop a runtime system to dispatch different kind of workloads to different compute substrates. So that's the 4 approaches that we have observed so far, but solution 3, solution 4 seems to be the most practical. So that pretty much covers what I want to talk about today. So today, to summarize, I talk about, first of all, congratulations, you guys are the lucky one. You are in the right era. Just wait for the next decade or two to see how this industry will thrive. Second observation is we don't have any yet very interesting applications for robots because we are still working on the basic building blocks. Third, talent supply is a key challenge today for the industry, for us as well. So we have to, we are actually a smart transportation company, if you want to call it. But we had to spend a lot of resources on developing systems to support our applications. That kind of sidetracked us a little bit in terms of resources and time. But that's the reality we have to face. So that's it. And thank you, Brian, and there are other organizers. I think it's a very exciting time, but I do hope that we can spend more time on closing the talent gap. Now it's a good time for us to chat and communicate.